Section 5.6. The Kasiski method. For over 300 years, the Belasso cipher was considered unbreakable. The French called it le chiffre indéchiffrable, the undecipherable cipher. The turning point came in 1863 when Major Friedrich W. Kasiski, a Prussian infantry officer, published a book detailing how the period of a polyalphabetic cipher could be determined. This is now called the Kasiski method or the Kasiski test. There is some evidence that Charles Babbage may have used the method in 1846, but did not publish it. Ole Emanuel Frankson of the Technical University of Denmark, who has written extensively about Babbage and his difference engine, wrote a book, Mr. Babbage's Secret, which makes this claim. The idea is to look for repeated letter sequences in the ciphertext. Some of these sequences may occur by accident, especially bigrams, but most of the repeated sequences will result from the same letters in the plain text being enciphered by the same part of the key. The longer the repeated sequence, the lower the probability that it happened by chance. If the same part of the key is used to encipher two repeated letter sequences, then the distance between them must be a multiple of the key length. Distance is measured from the first character of one occurrence to the first character of the other occurrence. Consider this cipher fragment using the keyword example. The ciphertext trigram PTR occurs 3 times at positions 5, 12 and 33. All 3 occurrences result from plaintext AIN enciphered with key characters PLE. That is, they result from the same plaintext trigram enciphered with the same part of the key. The plaintext trigram AIN, which starts at position 21, produces a different ciphertext trigram EMK because it is enciphered by a different part of the key, namely EEX. Likewise, the plaintext trigram THE, which occurs at positions 1 and 29, and the plaintext trigram INS, which occurs at positions 8 and 13, do not produce repeated ciphertext trigrams because they are enciphered with different parts of the key. In this fragment, the distances between the repeated trigrams are 12 minus 5 equals 7, 33 minus 5 equals 28, and 33 minus 12 equals 21. These distances, 7, 21 and 28, are all multiples of 7, which is the length of the keyword example. Kasiski showed how these repetitions can be exploited to reveal the period of the encipherment. Let's look at another example, a cryptogram. This is a Belasso encipherment of a text in normal English. Searching for repeated letter sequences, we find EK at positions 10, 64 and 90, RYR at positions 17 and 53, and so forth. The full list of repeated letter sequences is. We immediately notice 2 repeated tetragrams, YHCI and YXYR. Repeated tetragrams almost never occur accidentally. The distance between the 2 occurrences of YHCI is 79 minus 43 equals 36, and the distance between the 2 occurrences of YXYR is 69 minus 57 equals 12. The distances 12 and 36 suggest a key length of 4, 6 or 12. We can narrow that down by looking at some of the other repeated sequences. RYR has a distance of 36, and ZHZ has a distance of 6. The other repeated trigrams, HCI and XYR, are just parts of the 2 repeated tetragrams, YHCI and YXYR, so they yield no additional information. The most likely period for this cryptogram is 6. OK, that was a bit too easy. Let's look at what happens in harder cases. One method recommended in other books is to take all of the distances between repeated sequences and find all of their factors. The most frequent factor, they claim, will be the period. For example, if the distance is 36, then the factors are 1, 2, 3, 4, 6, 9, 12, 18, and 36. This could mislead you in several ways. First, you might falsely conclude that the period is twice its actual value. This is because about half of the distances will be even just by chance. Half of the valid distances, those caused by repeated sequences of plain text, will be even multiples of the period. For some messages, these even multiples of the period will outnumber those distances that are odd multiples of the period. Likewise, half of the accidental repeated ciphertext sequences will have even distances. There can be lots of even distances simply by chance. Similarly, 1/3 of the distances will be multiples of 3 by chance. When you count the number of divisors of the distances, you should reduce the number of times the factor 2 occurs by half, reduce the number of times the factor 3 occurs by 1/3, and so forth. This will give you a more accurate comparison. For example, if a distance of 3 occurs 6 times, reduce that by 1/3 to 4 times, because 2 of the 6 occurrences are likely to be pure chance. Second, when a repeated sequence occurs multiple times, the distances between pairs of these repeats may be misleading. If there are n repeats, then the number of pairs is n (n-1) over 2. In the example ciphertext, there are 4 occurrences of YR, so there are 6 pairs, that is 4 times 3 over 2 pairs. Hence there are 6 distances between pairs. 54 minus 18 equals 36, 59 minus 18 equals 41, 71 minus 18 equals 53, 59 minus 54 equals 5, 71 minus 54 equals 17, and 71 minus 59 equals 12. Which of these, if any, is a multiple of the period? Suppose that ciphertext XYZ appears 5 times, and that 3 of those repeats are due to the same plain text. There will be 10 distances, of which only 3 result from the repeated plain text, while the other 7 are spurious. You don't want to throw out the valid repeats just because you cannot distinguish them from the accidental repeats. Here is what you can do. Suppose that you have a candidate for the period. For example, suppose you suspect that the period is 6. Reduce the locations where the repeated sequence occurs modulo 6. Remember modular arithmetic? If not, look at section 3.5 again. Let's try the modulo method. Look at the 4 occurrences of YR again and reduce their positions modulo 5, modulo 6 and modulo 7 to see what happens. All 4 residues modulo 7 are different. If the period is 7, then all of the repeats of YR are accidental. There are only 2 equal residues modulo 5. If the period is 5, then only 2 out of the 4 occurrences come from repeated plain text. But if the period is 6, we hit pay dirt. We now see that the 4 occurrences of YR come from 2 different repeated bigrams in the plain text, one bigram at positions 18 and 54 in the plain text, with a distance of 36, and the other bigram at positions 59 and 71 in the plain text, with a distance of 12. How did that happen? Look back at the list of repeated sequences. You can see that the bigram YR occurs in the repeated trigram RYR and in the repeated tetragram YXYR. Each of these contributed 1 repetition. Let's look at a second method for determining the period of a polyalphabetic cipher. If the evidence from the repeated sequences is inconclusive, it is good to have a backup plan.